Hello everybody, can you hear me? Wow, it looks like the bit rate is pretty high. So, hi. Okay, it comes out. Right. Hello everybody. Thanks for your watching this is 8 p.m. on Saturday. And as I mentioned in the ED discussion board, this is going to be our last minute consultation for your midterm exam. So you can ask any questions as you like. So now, let's look at some existing questions asked by our students. So Nancy Lee, let's see, Nancy Lee is asking if we enter cumulative for 0 in a continuous distribution in Excel, what is the result for? All right. Now, actually, this is the concept about probability density function. Or PDF. And we know probability density function is for continuous probability distributions. Continuous probability distributions. And what is that for discrete? Do you remember? Discrete, I can't remember the spelling, whatever. But it's called probability mass function, right? So if you learn a little bit physics before, you probably know the difference between density and mass, okay? So if we define mass as our probability, the real probability, then for discrete distributions, the PMF is actually it actually looks like this, right? So if you plug in any number, for example, this is 5, and we can directly get the probability of x equal 5, for example, okay? So this is called probability mass function. So we can understand mass as the probability, okay? But now, what about density? What do you think of density? For any continuous distribution, for example, a normal distribution, okay? The probability density is actually described, for example, this is also 5, is actually the y value on this PDF. And it describes how likely can we observe a value around this value, okay? So, in terms of getting a mass, what do we need in physics? So if we want to calculate the mass of something, we not only need the density. So the density used to be written as rho, right? Rho multiplied by volume. So we need volume. That's why by integrating this probability density function from one value to another value, for example, from 5 to 6, we can get what is called probability mass, okay? So this is probability mass. But simply by plugging in one value, we only get the density at this point, okay? So that's how we understand the probability density function and probability mass function. And hopefully, Nancy Lee, this helps you answer your problem, okay? Xinxin He is asking, when can we know about the MIS exam computer device room number? Well, I think you probably apply for too late, so don't worry. I will send you the updating emails of the MIS semester exam computer device room number, okay? Week 6 tutorial. So there is a Xiaoyong Wang asking, in week 6 tutorial example question, now and alternative hypothesis 3, the manager claimed that the expected value will no less than 1,000. Okay, I think that is a common question for everybody, because I've heard some of you think that someone says if the manager claims something, and this must go to alternative hypothesis, and this is absolutely wrong. Okay, so never believe in that. The only way of determining null hypothesis and alternative hypothesis is to see where is the equal sign. Okay, where is the equal sign? So let's see, for this question, if the manager claimed that the expected value of the revenue will no less than 1,000. So this means his claim is mu greater or equal to 1,000. And the contradictory must be mu less than 1,000. So which one do you think has the equal sign? So this one has the equal sign, right? That's why we put null hypothesis as mu greater or equal to 1,000. But in our textbook, we just write equal sign, equal sign always, okay? So mu equal 1,000, but only in our textbook, because in other textbooks, we usually use mu equal greater or equal to 1,000. So this makes much more sense, right? But in our textbook, when you look at mu equal 1,000 and then versus mu less than 1,000, you can understand this as mu greater or equal 1,000, okay? So hopefully this will answer your question, but don't trust that if someone claims something, it must go to alternative hypothesis. This is something that I heard from our student, and it is wrong. Okay, I don't know where did you get those conclusion. Okay, but it's wrong. Only care about the equal sign. Okay, and the reason for putting equal sign into null hypothesis is because when we're constructing the test statistic, we always assume under H0, which means null hypothesis is correct, right? So in this way, we can actually, for example, if we get a Z, we can actually substitute a mu value into here, because under null hypothesis, mu equal 1,000, so we can use 1,000 over here, okay? So that's why it must contain an equal sign. But if there is no equal sign, we can not really plug in a value over here, okay? So equal sign. Now let's look at the question from Yanran Zhao. She's asking, we don't need to revise for two population. Yes, it is right. So there is no two population questions in your exams, okay? No two populations in the exams. Nancy Lee says thank you. Okay, you're welcome. Xinxin He says thank you. You're welcome. And makes sense. Thanks. You're welcome. Okay. Now let's look at a question from Sunny. Okay. She said, hi Tony, can you explain again when we need to use normal distribution and binomial distribution? Well, do you mean the normal approximation of binomial probability? If that is the case, I think there is another video talking about the normal approximation of binomial probabilities. But basically, when we are using binomial distribution, it is when we observe the repeating of what is called Bernoulli trials, right? Or Bernoulli experiments. So if we found some Bernoulli experiment in the question, for example, flip a coin, we can have a tail or head, right? Head or tail. So Bernoulli experiment is the kind of experiment that has only two outcomes. So if we repeat it for n times and we define the probability of something, we call it success to be P. And then we say the number of success. So if we define X to be the number of success, then X will follow a binomial distribution with N and P. Okay, so this is binomial distribution. But sometimes When we want to calculate the probability mass function for binomial distribution, for example, probability x equal something small x, and we know the formula is Cnx p to the power of x multiplied by 1 minus p to the power of n minus x. And sometimes if n is very large and x is very large, it is very, very difficult to calculate this value using a scientific calculator. So for example, if we want to calculate C1500, have a guess what value can we get from a scientific calculator. So I have one on my hand. So let's try and calculate this. So it's 1000 C500. And have a guess, what is the value? Error, okay? So it's not calculatable by a scientific calculator, okay? So not mention a human being, right? So it's not calculatable. Therefore, we use normal approximation for the binomial probability if n and p are large enough, which is np greater than 5 and n times 1 minus p greater than 5. In this way, the probability of x, or I can say x, can be approximated by a normal distribution with a mean np and variance np times 1 minus p. Okay, so this is when we use normal probability. But don't worry, if it is in your exam, it will tell you explicitly you need to use normal approximation to calculate the binomial probability, okay? So hopefully it answers your question. If it is not, please ask follow-up questions here, okay? Now let's look at the question from Xiaoyu Fu. Do we need to change our Excel into English version? You'd better change it into English version. But it's okay if you have a Chinese version, all right? So if you find Chinese version comfortable, just use it, okay? So Christine Shi, I think you're very active in ED discussion board. Thank you. So Christine Shi is asking, hi Tony, are we supposed to memorize the table for the number of classes in frequency distributions? If not, how should we decide when to round up and when to round down? Memorize the table for the number of classes in frequency distributions. Okay, you mean histogram, right? Well, I don't really think that you need to know it in that detail, okay? You know what I mean? So don't worry about histogram. I mean, there's no right or wrong answer for histogram. For example, if I want to have 6 classes and you want to have 7 classes, it doesn't matter. They both of them are histograms and they all show the frequency distribution. So nobody says 6 is better than 7 or 7 is better than 6. So there's no right or wrong answer. All right. Okay. Any other questions, guys? Oh, I think most of you have exam tomorrow, so that's why we don't have too many audience here. We only have 58 watching. I remember last semester it was over 100. Okay, but anyway. Mo Chun Li, Yo Shu. Okay, thanks. Any other questions, or you haven't started doing the revision? So please, come on. Questions. Anyway, I'll wait here till at least 9 p.m. So if you can think of any question, please ask. Because I remember last semester, I mean, there were too many questions, and I watched it. I answered it for like 1 hour and a half. I finally finished the questions, but why nobody asked any questions? Does it mean that everybody have learned QBUS very well? I think so. You all understand QBUS very good. Is there any practice questions for us to practice and prepare our midterm exam? Okay, is there any practice questions for us to practice and prepare our midsemester exam? Okay, as is mentioned by Autumn, the best practicing material is your Aplia homework questions. Some of the questions will look very similar to your Aplia weekly homework, okay? And another part of question is probably pretty much the same as our tutorial questions. Not the same, but similar, okay? Tutorial questions. Or end of chapter questions, okay? So tutorial questions, end of chapter questions, yes, Aplia homework, tutorial questions, or end of chapter questions. So those are the materials for you to do your revision for the mid-semester exam. So if you are very familiar with all those questions, I believe you can get at least 80% of the mark in your mid-semester exam, okay? Okay, so Victoria Fong asking, oh, well, let's see Christine Shi's question first, because Victoria Fong's question is a large one, okay? So Christine Shi is asking, expanding from my previous question, in textbook page 87, the Sturz formula gives 8.6 classes and the textbook chooses 9 classes instead of 8. Can you say in both 8 and 9 will be correct? Okay, I would say not both of them correct, but both of them are okay. This is not a black and white answer. This is not a question with a black and white answer. So 8 and 9, both of them are okay. But since 8.6 is closer to 9, so I would say probably 9 is slightly better than 8, okay? But I mean, it doesn't matter. It doesn't matter, really. Okay, so hopefully you're happy with my answer, okay? Now, Victoria Fong, how do I calculate? Okay, if during the exam you have to pick one, just pick the closest one. So round up if it is more than 0.5 and round down if it's below 0.5, I guess. Courtney Wang, how about 8.2? Okay, 8.2, you should probably pick 8, I guess. Yeah. So, Victoria Fong, let's look at Victoria Fong's question. How do I calculate covariance in Excel if we are given joint distribution? I think this is the question this is the sample question I post in our ED announcement, right? Okay. So expanding from my previous, no. So this is pretty much like, I think Victoria Fong is talking about a question that is in your Aplia, and it requires us a lot of time to calculate it. So we have the joint distribution of x and y. So y's value can be 1, 2, 3. X can also be 1, 2, 3. And we have some joint probabilities over here. And yeah. Can anybody think of any numbers? Or I'll just go to Aplia and look at the sample question. I think this is a good point. I don't know if you can calculate this, but I think it's very important. Where is it? Canvas? Yes. Please give me a second. I'll go to Canvas or Aplia to see the questions like this, modules. I'm still here, okay? Let me find a sample question. Okay, so if you are given this kind of joint distribution, in the question, for example, this is 0.03, 0.14, 0.44, and this is 0.16, 0.17, 0.00, 0.01, and 0.05, and 0.00. So all of those are the joint probabilities of x and y. And this kind of distribution is called bivariate distribution, which means two variable, okay, two random variable distribution, which is bivariate distribution. So if you are given bivariate distribution, there's very likely to be a question asking you the covariance between x and y, right? And in your formula sheet, this covariance is given by the expected value of x, y, and plus or minus the expected value of x times the expected value of y. You remember that? Okay, so what we can do is actually to calculate EXY first and then EX and EY. So EX and EY are very easy to calculate. You just get the marginal distribution of X and Y, right? So this is 19, this is 0.2, and this is 31, 36, and this is 44. And this is 5.1, and this is 3.3, and this is 0.06. Everyone happy with that? So all of those, this is the marginal distribution of y and marginal distribution of x. So you can easily calculate them either using Excel or you can just calculate it in your brain, right? This is a very easy calculation. So in this way, you can, if you are in Excel, you can use the sum product of this and this, right, to calculate EY or EX. So for EX, it is the sum product of 1, 2, 3 and 0.5, 0, 3, 3, 0.06. So it's just the sum product of this 1, 2, 3 and that probability, the marginal distribution, right? So you can just select this column and get EX. Or you calculate it using your calculator as well. So it is 1 times 0.51 plus 2 times 0.33 plus 3 times 0.06. So this is, what is it? 1.35. So EX now is 1.35. And now let's find EY together. So if you want to get EY, it is 1 times 0.2 plus 2.0.36 and 0.44, right? So we just do a 1.0.2 plus 2 times 0.36 plus 3 times 0.44, and we get, what is this, 2.24. So EY is 2.24. Everyone happy with this calculation? I think this is pretty straightforward, right? Now, what else? Okay. EXY. So EXY is a bit tricky because we need to find the distribution of x times y as a new random variable, x times y. So let's firstly see what are the possible values of x times y. 1, 1 is 1, 1, 2 or 2, 1 is 2, and 1, 3 or 3, 1 is 3, and 2, 2 is 4. And 2, 3 is 6, or 3, 2, and 3, 3 is 9, right? So we've got possible values of x, y, 1, 2, 3, 4, 6, 9. And then we need to find the probabilities of each in order to get the EXY, right? So xy equal to 1, the probability is only 0.03 over here. And if it is 2, it can be 1 times 2, or 2 times 1. So it's the probability of these two things. So it's 0.3, right? Okay, so 0.16 plus 0.14, 0.3. And if it is 1, 3 and 3, 1, it's gonna be 0.01 plus 0.04, which is 0.45. And for 4 is 2, 2. 2, 2 is 0.17. And just like that. 6, 2, 3, or 3, 2, 0 plus 0.05, 0.05, and 3, 3, 9 is 0. Therefore, you can simply calculate EXY by the sum product of this row and this row in Excel. Or you can calculate in your calculator 1 times, this is 1 times 0.03 plus 2 times 0.3 plus 3 times 3 times 0.45 plus what else, 4 times 0.17 plus 6 times 0.05, right? And you finally got 2.96. So in this way, you got EXY, you got EX and EY. So you add them all together, you get 2.96 plus minus 1.35 times 2.24. So you got 2.96 minus 1.35 times 2.24. And you finally end up with minus 0.064. Everyone happy with that? So this is how, when you're given a joint distribution, how can we calculate the covariance? So some of you probably ask, why can't we use what is called a covariance.s function in Excel to calculate this? But you can't, because this covariance is for our data. So if you are given 2 sets of data, you can calculate the covariance using this Excel function. But if you are given this kind of bivariate distribution, then you you can only calculate it by hand using the formula given in your formula sheet. Okay, so this is very important. Okay, so if you know it, just know it. Okay. So courtesy 1 is asking how about 8.2? Where? Okay. So now let's look at a question from Evelyn Zhao. Evelyn Zhao is asking, hi Tony, the answers after the textbook were given by Gao. Are these answers all correct? Because I find some answer might not correct, but I'm not sure. Okay, I think just trust yourself, okay? Because Gao is, yeah, I know it's probably not correct, but can you give us some examples of those incorrect answers? Okay. Nancy Lee is saying, I remember Aprilia has an answer around 5.52 to 54 to 5. Oh, really? But forget it, okay? Don't worry. Victoria phone message retracted. Okay. Daiwen Wei is asking, how many ways are there for us to test the independency of 2 events? Okay. Independency of 2 events. Well, if you still remember, there are 2 ways to test the independent events, right? So the first one is that if the probability of, for example, x and y equals the probability of x times the probability of y, then they are independent, right? And secondly, if the probability of x given y equal to probability of x, then we can say x and y are independent. Okay, so those are the 2 ways. So if the joint probability equals the margin, the product of the marginal probability, then those two variables are events are independent. And also, if the conditional probability equals the marginal probability, then we can also say they are independent. But one thing, when we are applying this rule, let's look at an example. So sometimes it will give you something like this: y1 to x, 1, 2, right? So this is, again, a bivariate distribution. And they probably ask if x and y are independent or not. So let's make up some numbers, okay? 0.2, and this is 0.1, and this is 0.3, 3, and this is 0.2, 2, 3, 4, 4, right? 1, 2, 3, 4 is 10. Okay, so for example, if we are given this kind of bivariate distribution again, and we are asked if x and y are independent or not, okay? So if x and y are independent, we need every single one of the joint probability must equal to the product of their marginal probability. You know what I mean? All of them must equal to the product of the marginal probability. But if we want to test if they are not independent, we can only find at least one of the joint probability not equal to the product of the marginal probability, and then we'll be fine, okay? So now let's look at some possible results. So this is x and y value 1, 1, 1, 2, 2, 1, 2, 2. Those are 4 possible results, right? And we can find their joint probabilities as well as the product of their marginal probabilities. You know what I mean here? Yes, so let's now first find out the marginal distribution of x and y. So this is 0.5, and this is 0.5, and this is 0.3, and this is 0.7, right? So now first, when x equal 1, y equal 1, the joint probability is 0.2, right? And the marginal probability, or I mean the product of the marginal probability is 0.15. So they are not equal. Therefore, we can say x and y are not independent, okay? So if you want to make, if x and y are independent, all of the possible combinations of x and y values must satisfy the joint probability equals the product of the marginal probability, okay? So if you find at least one of the joint probability does not equal to the product of the marginal probability, then x and y are not independent, okay? Yeah, so this is how we determine two events or two random variables are independent or not. Okay, let's look at some new questions. Courtney Wang, are you hungry? I just finished my dinner, so I'm not. Hui-Wen Liu is asking first line should be 0.61. Which one? 0.61. Really? Yeah, this is 0.61. Sorry. Okay, but anyway, you know what I mean, right? Is it 6.1? 5. Oh, yeah, it's 6.1. Yes. Yes, you're right. Sorry. My bad. But it doesn't matter, okay? So I know my result is wrong, but you know how to calculate, right? Okay, don't trust my brain. Yu Yifan is asking how long will this live streaming be? I mean, I'll stay here at least to 9 p.m. But it will end when I answered everybody's question. Okay. Ruchi. Ruchi is asking, could you please go through p-value and rejection region again? Well, so for in terms of p-value in rejection region, well, again, we are when we are making a decision rule, making a decision if we wanna reject or not reject the null hypothesis. I mean, this is a very big question. For example, mu equals, let's just take that 1000 as an example, okay? And mu less than 1000. So if we want to make a decision, if we reject or not reject the null hypothesis, we are actually observing the test statistic, right? And for example, if a test statistic is z, and it is calculated by x bar minus mu divided by sigma divided by square root of n. So for example, we know the population variance, okay? And we are actually observing x bar and calculate z. And we want to see if this value is very far away from 0, right? Because we want to know if x bar is very far away from mu under null hypothesis. So this is 0, and you can see if we observe a z over here, and this is not very likely if if null hypothesis is correct, because it's outside of the very likely region. So we call this region the rejection region. Therefore, for one-tailed test, okay, I think what you want, I think you probably want me to summarize the decision rules. So if it is a two-tailed test, let's start from a two-tailed test. So if it is a two-tailed test, we will reject null hypothesis if our test statistics, the absolute value of the test statistics, it can be z or t, okay? So what about I use theta over here? So I call theta a test statistic, okay? Any test statistic. So if the observed value of theta is greater than the critical value, and then we reject null hypothesis. And if it is the right-tailed test, it is when theta observed are not absolute, greater than theta critical, we reject null hypothesis, right? Reject. And if it is a left-tailed test, and then if the observed value of theta less than the critical value, we reject the null hypothesis, okay? Reject null hypothesis. So this is when do we make our decisions. So it makes sense if you draw the diagrams, okay? So you can see if it is a two-tailed test, so this is the critical value. For example, this is z, okay? This is z critical value. And then if you observe something around here, we reject null hypothesis, right? So in this way, our observed z is greater than that's critical. Or if we observe something at z over here, it is less than the minus of the critical value, or it's still the absolute value is greater than the z critical value, we also reject the null hypothesis, okay? So this is about two-tailed test, and one-tailed, same thing, right? Now, for p-value approach, if it is a p-value, let's see, they are actually equivalent things. So if we observe a z over here, and we know the probability to the right-hand side, if it is a two-tailed test, then the p-value is equal to 2 times the probability of the z observed value greater than the critical value. The z greater than the absolute value of the z observed value, right? So this is how we calculate the p-value for two-tailed test. And it basically means the probability to the right-hand side of this value and the probability to the left-hand side of the -1 value, okay? So two of them add together. This is because we want to compare this p-value with alpha. We want to see if it is greater than alpha and less than alpha, because those two probabilities outside the critical values add together is alpha, right? So if we compare this value with alpha, if it is greater than alpha, this means the value we observed is in this region, right? Because the probability is greater than this, right? So we do not reject. So we do not reject null hypothesis. And if it is less than alpha, this means we are observing a z observed value outside, inside the rejection region, because this probability is much less than this probability, right? So we reject null hypothesis. So this is for two-tailed p-value, okay? Two-tailed p-value. And if it is a right tail or left tail, things becomes much easier. So if it is a one-tailed p-value, and this p-value can either equal to the probability of this observed, a normal random variable greater than the observed value or less than the observed value. It depends on if it is right tail or left tail, right? And again, if it is greater than alpha, do not reject null hypothesis. And if it is less than alpha, reject null hypothesis. And it's also very obvious in the diagram here. For example, if it is a right tail test, and our critical value is here. This is Z, for example, Z alpha. And we know if we observe something here, we reject null hypothesis, right? And we observe something here, we do not reject the null hypothesis. So we can see the probability to the right-hand side of this observed value is less than alpha over here, right? So the whole probability is alpha. So when this probability is less than alpha, we reject the null hypothesis, okay? So less than alpha, reject null hypothesis. And if it is greater than alpha, we do not reject null hypothesis, okay? So this is basically how do we make a decision for under p-value approach and rejection region approach. And they are equivalent approaches. But the most important thing is you need to understand what is hypothesis testing. And it takes another tutorial for me to explain to you again. So hopefully you can read some textbook if you don't understand, okay? Read the whole process of hypothesis testing. But so far this is rejection region and p-value approach, okay? Cloris Hu is asking, when can we use the formula of calculating the sample size in which the standard deviation is 0.5? It's when proportion. When we are estimating a proportion, we do not know sigma, right? So I know what you mean. So in your formula sheet, we have these two formulas. One is Z half an alpha sigma divided by b square, and the other one is Z half an alpha 0.5 b squared. So this sample size determination is when you are estimating estimating population mean mu, and this is applied when you're estimating population proportion, okay? Because here is supposed to be, if you were in my tutorial, here is supposed to be the p times 1 minus p b square, right? So because we do not know the value of p, so the only thing we can do is to try to make this value as large as possible by taking p as 0.5. So we have 0.5 times 0.5 over here, and if we take inside the square, we got 0.5 over here, okay? So this is when estimating proportion, and this is for estimating mean, okay? Thank you for your question, Cloris Hu. And Lian Yang is asking, what is the difference between ordinal and interval scales? I saw an explanation that ordinal scales make things in order, but the difference aren't meaningful. Interval scale subtract is meaningful. Okay, so this can be done. Let me show you an example of an interval scale and ordinal scale. So if it is an ordinal scale, it can measure your, for example, if I want to measure your exams result. So you have HD, you have D, you have credit, and you have pass and fail, right? So if this is called ordinal scale. We know HD is better than D. D is better than C. C is better than P. P is better than F, right? But it doesn't make sense if you want to know HD minus D. So what is the difference between HD and minus D? It doesn't make any sense. So this is ordinal scale. But if it's a interval scale, it is marks like 87 and 82, and the credit, let's get a 67 and 53 and 48. Now, you will know the difference makes sense, right? So we know this student is 5 marks higher than this student. So 87 minus 82 makes sense. It's 5 marks. So we know this student get 5 more marks. But if you simply know the grade of those two students, HD and D, and we can't really tell the difference between those two students. It can be the difference between 175, right? But it can also be the difference between 85 and 84, right? So HD and D doesn't make any sense, but the only thing we know is that HD is better than D, okay? So this is called an ordinal scale, and this is called an interval scale or numerical scale. I hope this question I hope I answered your question correctly. And Yanren Zhao is asking, there is an Aplia question. If P equals 0.001, why can't we conclude that there's strong evidence to infer that the alternative hypothesis is true? Why can't we? There's strong evidence. Well, if that is a question, I think we probably don't talk strong evidence that much. We always say sufficient evidence or insufficient evidence, something like that, right? But when it is strong evidence, I don't think so, but yeah. But don't worry about that kind of question, okay? Probably in your exam, you only know can we conclude or not, okay? This is in too much details, this kind of question. All right. Shengrong Li is asking, where is it? Hi, what is the clear line between overwhelming evidence and strong evidence in one question about p-value to judge hypothesis of p-value? Overwhelming, strong is wrong. Or can you generally explain all the questions apply hypothesis testing, the rejection region method, and the p-value approach? I'm confused every time I do this chapter. Okay, don't worry about overwhelming evidence or strong evidence. Actually, if you read your textbook clearly, there probably something like when you are given a p-value, there are probably some threshold for strong evidence or overwhelming evidence. But we only test you're only tested on the things that you learned in your tutorials and lectures, right? So if you read the textbook carefully, I think you can probably get the answer. But I don't have a textbook with me, so I have no idea why sometimes it's overwhelming evidence and why it's strong evidence. But I'm pretty sure when I was doing a clear question, I will do each question with the textbook. So after read one chapter or one unit of the textbook, I finish one small question, and it helps a lot. So it probably in your textbook, but it's not covered in our lectures. So Courtney Wang is asking, do we need to input some numbers, or there are just some choices for us to choose like a clear question? Both, okay? My answer is both. You do have choice questions, but also you have number input questions, okay? Yuan Liu is asking, can you please explain the central limit theorem? Okay, for central limit theorem again, CLT, central limit theorem, is actually telling us the sampling distribution of sample mean x bar, right? Because we know x bar is a random variable, okay? So x bar is a random variable, it must have its own distribution. So central limit theorem is basically telling us if no matter how the population is distributed, or the population can be any distribution, right? As long as n is greater than 30, then the sampling distribution of sample mean can be approximated by a normal distribution. And the mean of this normal distribution is the population mean mu, and the variance of this distribution is sigma squared divided by n, Okay, so this is basically what central limit theorem tells us. Okay, and again, if some of you might ask, what if n is not greater than 30 and n is less than 30? What can we do? If we still want to use a normal approximation, then we must require a normal population. Okay. So the population, if the population is normally distributed, then x bar still follows a normal distribution with mu and sigma squared divided by n. Okay. So those are two scenarios. If the sample size is large, then the population distribution can be any distribution, and sample mean will always follow normal distribution. But if it is a small sample, and we need to require the population to be normally distributed in order for x bar to be normally distributed again. Okay, so this is basically what is a central limit theorem. Okay. Yanran Zhao is asking, if the question does not mention that the population is normally distributed and sigma is unknown, can we use student t? So you will see if you need to see if the sample size is greater than 30, right? So if sample size is greater than 30, you can still use student t distribution. Okay. So again, t distribution is just a more detailed or a generalized form of normal distribution, right? So basically, if sigma is unknown, then x will follow a t distribution, right? With degree freedom n-1. Again, this is the same. If sigma is unknown, x bar follows a t distribution with mean mu and variance s squared divided by n. And this is mean mu s squared divided by n, right? So this is when sigma is unknown, okay? If the question, okay, Evelyn Lee, hi Tony, could you please explain Chebyshev's theorem? How does it relate to normal distribution? Okay, Chebyshev's theorem, is it a formula like 1 minus 1 over k squared? I can't remember exactly because it's been a long time. I haven't touched this kind of thing. So what is Chebyshev's theorem? Let me Wikipedia it, okay? Chebyshev's rule. Let's see. Okay. Empirical rule, Chebyshev's theorem. Where is it? Where are you? Okay, I got it. All right, so for Chebyshev's rule, or inequality, it is basically telling us that at least this many of percent of the data will fall within any distribution. Okay, any distribution with k sigmas. Okay, k sigmas. So this means for any distribution, but this requires k must greater or equal to 2, because if k equal to 1, it doesn't make sense, right? But it means at least. So at least means 0 is at least 0, right? Okay, but anyway, so basically, if we look at any distribution, okay, for example, this is any distribution, and this is the mean of the distribution. So from Chebyshev's rule, if we input 2 over here, so we got 1 minus 1 over 4, right? So if we k equal 2, this we got 1 over 4, which is 75%, isn't it? So it means 75% of the data will fall between the mu minus 2 sigmas and mu plus 2 sigmas. So K is 2 here, right? 2 sigmas. Happy with that? So this is 75%. I mean, at least, okay? At least 75% will fall within this area. And when K equals 3, you can see it's 1 over 1 divided by 9, 1 minus 1 divided by 9. It's around 88.9. It's 88.999 or 888. It should be 88.888, but anyway, it's something, right? So it means roughly 90% or 88% or 89% will lies between will fall into the mu plus 3 sigmas and with between minus 3 sigmas and plus 3 sigmas. Okay, so within this area it's around 88.888, but it's never precise. Okay, it's just an estimation. Okay, so so generally speaking, 1 minus 1 divided by k squared percent of the data in a distribution will fall within k sigmas around its mean. Okay, so this is what Chebyshev rule is telling us. Okay. Courtney Wang is asking, do we need to remember empirical rule? And is it approximate number using normal distribution? Okay, Evelyn Lee still asks, how does it relate to normal distribution? It has nothing to do with normal distribution, okay? It applies to any distribution, because for normal distribution, we have our empirical rule. It's like around 66% in 1 sigma, and some other person in 2 sigmas, and some other person in 3 sigmas. Anyway, but I can't remember the number exactly. So you can see I don't need to remember. So do you think you need to remember it? Okay. G of L, so confusing. What is so confusing? Can you specify what is so confusing? Thank you. Emily Cow is asking, good evening, Tony. When mu is given, for example, 20, the question is what the mean of X bar is. The answer choice including A, 20, B equal to the population mean. Why choose B rather than A? Okay. So Emily Cow, for your question, you must misunderstand the question, because if mu is given, I think 20 is not mu. 20 must be sample one observation of sample mean. So it must be a sample mean X bar. It's not mu. So in this way, we need to choose equal to the population mean. Okay, because the mean of X bar is always the population mean, right? But if when mu is given, it will not have this kind of question, okay? It must be 20 if mu is given to be 20. So this 20 must be a sample mean. It's not a population mean, okay? All right, Courtney Wang is asking, will we have some definition question like definition of parameter? I don't know. But for definition questions, my suggestion is you need to understand the definition, okay? Never memorize it. This is different from your overseas studies. Even if we test on your definitions, we will test on your understandings instead